Okay. Okay, so just read the question. In this question, what you have to do, a rectangular beam of width 350 millimeter is subjected to a uniformly distributed load of 15 kilonewton per meter over an effective span of 8 meter. Determine the depth required for the beam and also calculate the area of tensile reinforcement required. Okay, so M20 and Fe250 steel we have to use. Okay, so now we have to see what is our final aim. We have to find out the depth required. Okay, total depth we have to find out, and also we need to find out the area of steel. Okay, so so first our B is given, width of the beam is given, this is the width of the beam. Then a UDL of 15 kilonewton per meter is acting on the beam for a span of 8 meter. So we can find out the maximum bending moment for that UDL. The formula is WL square by 8, which we have already discussed. Okay, so you have got the moment of this much. Okay, so now since M20 concrete is given from table number 21 of IS 456, you can find out sigma CBC is 7. And for Fe250 steel from table number 22, you will you can find out the value of sigma ST. Okay, so all of you must know what is the difference between sigma ST and only sigma S. Okay, so here you can see we have to find, okay, sigma ST means it is the permissible stress in steel. That means it is the maximum amount of stress that can be developed in Fe250 grade of steel. Okay, and whose value is given in the IS code, it is 140 Newton per millimeter square. Okay, so after getting these two values, we can find out the value of modular ratio by this formula. See the value. Then we have another formula to find out the value of K. This formula which you have already discussed in the previous classes. K. After getting the value of K, you can find out the value of J also. J equal to 1 minus K by 3. This is the value. Then we can find out the value of R. R means half sigma CBC K into J. This is the formula of finding out the value of K. Okay, this is the formula to find out the value of K. This is the formula you can find out K. Okay, so after getting the value of K, our J value is 1 minus, this is J equal to 1 minus K by 3. This is the PDF which I have shared with you, not in the last week, I think before that I have shared with you this PDF. Okay, so after getting the value of J, we are trying to find out the value of R. Okay, your R is half sigma CBC K into J. This value we are going to find out. Okay, so you can see R value is this much. Okay, so now we need to find out the minimum effective depth required. Okay, so we know that moment of resistance equal to RBD square. Okay, moment of resistance formula is RBD square. All of you know that RBD square, this is the value of moment of resistance, this is the formula. And also we know that moment of resistance is nothing but the maximum bending moment. Okay, so maximum bending moment equal to moment of resistance. Okay, so we know the value of maximum bending moment, which we have already calculated, 120 into 10 to the power 6. This is the value of maximum bending moment. Okay, so if you put the value here, M is 120 into 10 to the power 6. We know the value of R, which is 1.21. We know the value of B. Our aim is to find out the value of D. So I hope all of you can find out the value of D from this formula. Okay, so now we have got the value of D is 532.3, which is difficult to provide. So let us assume that we are providing 535 millimeter. Okay, effective depth. Okay, so now it is asked to find out the depth required for the beam. That means we have to find out the total depth, not the effective depth. Okay, we have to find out the total depth of the beam. Okay, so we know that the total depth is equal to effective depth plus clear cover plus diameter, half the diameter of bar, or directly you can say total depth equal to effective depth plus effective cover. Okay, so here you can see total depth equal to 535, which is your effective depth, plus 25 plus 10. You can see here, assuming clear cover equal to 25 millimeter and diameter of bar equal to 20 millimeter. Okay, so if the diameter of bar is 20, we have to take half the diameter, that is our 10, and clear minimum, assuming clear cover means it is the distance between the bottommost layer to the surface of the reinforcement. Okay, I will show you here again. This figure I have showed so many times. Yeah, this much. If you take directly effective cover, you have to take 25 plus 10, 30, 35. Okay, but clear cover means this much distance from the bottom of this reinforcement to this portion. From this surface, from the surface of the steel to this layer, it is called our clear cover. Okay, and if the diameter of this bar, this is our bars, steel bars, in this case we have taken that the diameter of bar is 20, so we have to take half of the bar, half of the diameter, so it will be 10 plus clear cover is 25, so 35 plus this D, which is our effective depth, which we have already calculated, 535. Yeah, 535 plus 25, it is our clear cover, plus 10 is the half of the diameter of the bar. Okay, so we have got the total depth of the beam is 570. So now we need to find out the value of AST. AST equal to, you can find out by moment of resistance divided by sigma ST into J into D. Okay, so this way we can find out the value of AST as well as total depth of beam. Okay, so all of you have seen the problem. So now, do you have any doubt in this problem? All of you, do you understand this problem? All of you? All of you, do you understand this problem? Yes, sir. Okay. It is not a very hard problem. Almost everything is same. Only you need to remember which formula we have to use. Okay. When we have to use which formula, we have to know that one. Okay. So now these are the all problems regarding our singly reinforced beams. So now we are going to see what is doubly reinforced beam and why we need to provide doubly reinforced beams. Okay, so this is our doubly reinforced beams. Doubly reinforced beam. Yeah. You see read the introduction part. The RCC beam in which steel reinforcement is placed in tension as well as in compression zone are called as doubly reinforced beams. The moment of resistance of a balanced section is, we know the formula. If the dimension of the beam is B into D, this is the formula, RBD square. Okay. So sometimes what happens, due to headroom constraints or architectural configuration, the size of the beam is restricted and your beam might need to resist more amount of moment. So in this case, we have two options. Either we will use over reinforced section or we will use doubly reinforced section. Okay, so over reinforced section is not economical and also it is not safe because this kind of beams will fail suddenly without giving any warning time. Okay, you can see here option 1 is not a good choice. Over reinforced section are economical and failure of these beams is sudden without warning. Okay, so therefore it is better to use doubly reinforced beams. Okay. The extra steel provided in the tension as well as in compression zone resists the extra moment. Okay. So the main reason of using this doubly reinforced beam is when the size of the beam is restricted. That means due to, say, since if you don't have sufficient space, so in that case we will first fix the size of the beam. That means, say, we are going to provide this size of the beam. So in that case, if you are providing a singly reinforced beam, you can see that in some cases, the moment which is developing within the structure is more than the value of RBD square. That means whatever the size of the beam, it might need to resist more amount of moment. So in that case, if you provide reinforcement only on one side, since the moment is actually bigger than RBD square, so your beam might fail. So in that case, to resist the extra amount of moment, we have to provide extra reinforcement both in the tension as well as compression side. Okay, and those reinforcements will resist the extra amount of moment. Okay, so now you can see here, by two ways we can resist the extra moment. One is our first option we have by using a doubly reinforced section, and the second option is by using a doubly reinforced section. So we will never go for over reinforced section, because if you go for over reinforced section, this will become uneconomical, and also the failure of these beams is sudden. That means it will not give you any warning time and it will be very risky. So we will never go for over reinforced section. So only option we have is using doubly reinforced section. So you can see here, therefore it is better to use doubly reinforced beam in such circumstances. And the extra steel provided in the tension and compression zone will resist the additional moment of resistance required. Okay, so this is the main reason of using a doubly reinforced beam. Okay, so there are other reasons also. These are the other reasons. Okay, so I'm not going through all of this. Okay, so next we have to see how to analyze a doubly reinforced beam. Steps are exact same, only the formulas will be different. Okay, steps are almost 100% same with the singly reinforced beam, only the formulas will be different here. Okay, so let us see the procedure by which we can analyze a doubly reinforced beam. Okay, so first we have to see modular ratio. What is the difference between modular ratio of a singly reinforced beam and a doubly reinforced beam? You can see here we have to find out two types of modular ratio in case of doubly reinforced beam. One is modular ratio for tension steel. That means for the reinforcement which is provided in tension side, we have to find out modular ratio, and which is same with the singly reinforced beam. This is the value which we have already used so many times. M equal to 280 divided by 3 sigma CBC. And again, after getting the value of M, we have to find out the modular ratio for compressive steel also, and it will be denoted by MC, and it is taken as MC equal to 1.5 times of this value. M for modular ratio, C for compression. Okay, M for modular ratio, C for compression. That means this is MC will represent the modular ratio for compressive steel. Okay, and only if you write M, then it will indicate the modular ratio for tension steel. Okay. Okay, so now you can see the formula. Okay, directly we will go through the formula. You can see here the stress in compressive steel. Okay. Critical neutral axis, same formula. Critical neutral axis, same formula, which we have used in the last class and in the previous problems. We need to find out the critical neutral axis by the same formula. Only the difference will come when we have to find out actual neutral axis. Okay, so you can see the formula, this one. So in this entire formula you can see one thing is coming extra. That means this bn square by 2 in the singly reinforced beam, bn square by 2 equal to this part, m into ast into d minus n. This was the formula for singly reinforced beam. In case of doubly reinforced beam, this portion will become extra portion. 1.5 times of m minus 1 ASC. ASC means area of steel in compression. That means if you provide two bars of say 16 mm diameter in compression side, that means at the top portion of the beam, so ASC will be 2 into pi by 4 16 square. Simply ASC means area of steel in compression. Okay, so n means your actual neutral axis depth, and d dash, this d dash means it is the, I will show you the diagram. This is the value of d dash. You can see this is the value of d dash. D dash means it is the depth of reinforcement from the topmost layer. Okay, and this dimension you have to take from the topmost layer, from this level to this, from this level to the center of the reinforcement. Okay, from this top layer to the center of the reinforcement, that will be known as our d dash. That means it is the effective depth for compressive steel. Okay, and this d will be known as effective depth for tensile steel. Okay, this d will be known as effective depth for tensile steel or tension steel. Okay, because you have measured the distance from the top to the center of the tensile steel, and this d dash will be known as effective depth for compression steel. Okay, since we are measuring the distance from the top to the center of the compressive steel. Okay, so this d dash is from the top to the center of the reinforcement. Okay, so this is the formula to find out actual neutral axis, and this is the formula to find out critical neutral axis. Same formula with the last one. Okay. Okay, so now here you can see the stresses of a doubly reinforced beam as shown in the figure 2.7c. Yeah, this figure you can see here. At the topmost layer, we know that the value will be sigma CBC, which we have already discussed in the singly reinforced beam. But now, since steel is present in this level at d dash depth, so there will be a stress here. Okay, this value we will represent by sigma C dash. Okay, sigma for stress, C for compression. Okay, so it is the stress in steel in compression, stress in steel in compression. Okay, this value sigma C dash. Okay, and the other portions is same, other portions are same. This height is, this height was our d dash, so this height will become d minus d dash, because our from this level to this level the total height was our d effective depth. This height was our, this portion was our d dash, this value. Okay, so this portion will become d minus d dash. Okay, so now you see here the maximum compressive stress in concrete, you know that the value is sigma CBC. The stress in equivalent concrete at the level of compression steel, it is sigma C dash. Okay, next we know this value sigma ST by m. Stress in equivalent concrete at the level of steel, this is tensile steel. Okay, then stress in compression steel MC into sigma C dash. MC value is 1.5 times of m. Sigma C dash is the stress in compressive steel. So this will, we will represent this as sigma SC. Next, stress in tensile steel, we know the value sigma ST. Okay, so now you see the moment of resistance. How you have to find out moment of resistance? So the moment of resistance of a doubly reinforced beam is taking the moment of compressive forces about the circuit. You can see the total moment of resistance will be m1 plus m2. Okay, So M1 will be, you can see here, M1 will be the moment of the compressive force in concrete about the tensile steel. This is the formula which we have already used in the last class, in the previous numericals. RBD square, same formula M1. Okay, and this M2 is the extra amount of which I have been saying that in W reinforced beam we have to resist extra amount of stresses. This is the extra amount of stress which we have to resist, and the value is C2 into D minus D dash. Okay, the value of C2 is this value. So the moment formula for moment of resistance is M1, this formula, plus this value. You see here, MR equal to M1 plus M2. MR value is this one, M2 value is this one. These are some simple derivations. No need to remember these derivations. Only we need to remember this formula. Okay. M means nothing but the previous formula which we have used. B is the width of the beam, sigma C dash, stress at this level. Okay. So these are the various types of problems which we will discuss in this in this part. Are same with the last class, same with the previous one. In the first kind of problems, we will determine only the moment of resistance. In the second kind of problems, we will determine the actual stresses in concrete and steel. And in the third type, which is the most important, we have to design the section. That means what will be the width of the beam, what will be the depth of the beam, everything we have to design here. Okay. So these are the three types of problems which we have to discuss in W reinforced beams. Okay, so in the first kind of problems, that means if you are asked to find out moment of resistance, then almost all the values will be given to you. You can see the given values will be the width of the beam will be given, effective depth of the beam will be given, then AST will be given, ASC will be given. Almost all values are given. Okay, only we need to use the formula and we need to find out the moment of resistance. Okay, so you can see here in W reinforced beam also we will have balance section, under reinforced section, and over reinforced section. Okay, so now for see here, first we need to find out actual neutral axis and critical neutral axis by these two formulas, this formula and this formula. Okay, by this formula you will get critical neutral axis, by this formula you will get actual neutral axis. Next, similar to the previous problems, we have to compare the values of actual neutral axis and critical neutral axis. So if depth of actual neutral axis N will be more than NC, critical neutral axis, then the section will be under reinforced like the previous problems. Okay, so in that case our moment of resistance formula will be this one. This portion is our M1 and this is our M2. M1 plus M2. M1 means if you, okay, so what is the difference between a singly reinforced beam and doubly reinforced beam? In the doubly reinforced beam, you are providing reinforcement in the compression zone also. Okay, so this is the amount of moment which your beam will resist only if you provide reinforcement in tension side, and this is the amount of moment which the beam will resist when you are providing our steel in compression side. Okay, so if you add these two values, then you will get the total moment of resistance, M1 plus M2. Okay, so this is the formula for finding out moment of resistance for a under reinforced section. Okay, so next, if N is greater than NC, then your section will be over reinforced. Then This is the formula to find out moment of resistance. Okay, so you compare these two formulas, you will see what is the difference. What is the difference? No difference. No difference. You can see in this formula, this sigma c dash, that means stress in the compressive steel level will be this value. Okay, but in this case, when the section will be over reinforced, so in that case you see the value of sigma c dash. Other things are same. Sigma cbc will be same, b will be same, n will be same, d will be same, m will be same, a, c will be same. Everything is same. Only the difference will come in the value of this sigma c dash in both the formula. You can see the values. This is sigma dash cbc. This is sigma cbc. So sigma cbc, that means it is the maximum stress which will be developed in concrete. That is our sigma cbc. And sigma dash cbc is the maximum compressive stress developed in concrete in the compressive steel level. Here, at this level, what will be the maximum compressive stress will be developed? That will be written by sigma dash cbc. Okay, and at this level you know that the stress will be maximum, which will be written by sigma cbc. Okay, so this is the difference. So when we will solve the numericals, it will be better to understand. So let us go to the numericals. First numerical. Yeah, see this numerical first. Examples of problem type 1, determination of moment of resistance. Okay. Okay, and one thing, those who are attending the first class, if you are absent in the second class, you are not getting the attendance. Okay. If you want to get the attendance for both the classes, you have to attend both the classes. Okay. Okay, so let us see the problem. You can see in this case you can see the section of the beam is given 400 into 600. Then it is also mentioned that you are using 425 millimeter bars. That means this is the number, 4 number of 25 millimeter diameter bars on tension side. You are using 4 bars of 25 millimeter bars on tension side. That means at the bottom of the section you are providing 4 numbers of 25 millimeter diameter bar and 4 20 millimeter bars on compression side. That means, and in the compression side, that means above the neutral axis, you are providing 4 number of 20 millimeter dia bars. Okay, so you are asked to find out moment of resistance of the beam. Use M20 concrete and Fe 415 steel. Take effective cover to the center of this one and okay. So I will show you the diagram how it will be. Okay, see here. In this problem, okay, I will show you the problem again. In this problem, the width of the beam is given, the effective depth of the beam is given. This D is given, this width of the beam is given. I think 400 by 600. Then it is said that you are providing 4 bars of 25 millimeter bar in the tension side. That means these are the bars in the tension side. And also you are asked that it is given that you are providing 4 bars. Okay, this is the simple diagram, but in this problem we are providing 4 bars here. There will be another dot here. Okay, you are providing 4 bars of, here it is 3, but in this problem we are providing 4, so another dot will come here for that problem. So in this problem we are providing 4 bars of 20 millimeter diameter bar in the compression side and 4 bars of 25 millimeter dia bars in the tension side. Okay, and another thing is given that this effective depth to the compressive bar is given, I think 40 millimeter. You see the value. Take effective cover to the center of compressive reinforcement as 40 millimeter. That means D dash value is given. Effective cover means whenever the word effective is mentioned, that means always you have to understand the measurement is taken up to the center of the reinforcement. Okay, whenever the effective word is mentioned, you have to understand the distance is taken up to the center. Okay, so since this D dash is nothing but the distance from the topmost layer to the center of the reinforcement, and this is known as effective depth for compressive reinforcement, and this value is given 40. Okay, and so now in this case we need to find out the value of moment of resistance. Okay, so first we have to find out sigma. First we have to find out depth of actual neutral axis, that is our n. Then we have to find out critical neutral axis. Then we will see whether it is under reinforced or over reinforced. So, and then we will use the formula of moment of resistance. Okay, similar to the previous problems in single reinforced beam, procedure is exactly same, only the formulas will be different here. That's the difference. Nothing is except that there is no other difference. Okay, okay, so let us solve the problem now. I hope all of you are writing. Okay, I hope all of you are writing. Write down the problem and try to solve it. Okay, try to solve it. I am showing you the answer also. B is given. Okay, so our class will be over within 5 minutes. Okay, D is given. This is 400, this is 600. This is our B, this is our small d. Effective word is mentioned, that means it is the value of small d. Then D dash is given 40 millimeter, this value 40 millimeter. Then AST, area of steel in tension, you are providing 25 millimeter bars, 4 numbers, this value. 4 bars of 25 millimeter bars in the tension side, this AST. Then for again ASC, area of steel in compression, you are providing this 4 numbers of 20 millimeter dia bars, 4 into pi by 4, 20 square. Then sigma CBC, we can find out from table number 21, because your grade of concrete is given M20, and from the grade of steel you can find out sigma ST from table number 22. Okay, so next procedure is same procedure. We have to find out critical neutral axis from this formula, which you have used so many times, more than 10 times. Okay, so from this formula, if you calculate, if you put all the values, you will get critical neutral axis is this much. Then actual neutral axis formula is this one. I have shown you the formula. This one. Okay, all values are given. B is given, M is known, ASC is known, D dash is known, everything is known, only unknown is N. That means depth of actual neutral axis is unknown. If you put all the values, you will get the value of actual neutral axis. Okay, put all the values, solve it, you will get the value of N equal to 189. Okay, so now you compare these two values, you can see actual neutral axis depth is more than critical neutral axis depth. That means our section is over reinforced. You can see here, over reinforced. So sigma CBC will be 7 Newton per millimeter square. So this is the formula to find out sigma C dash. So moment of resistance formula is this one. Okay, for the next class also your link will be same. Okay, with the same link you can join for the next class. Our first class will be over now. For the second class you can use the same link. which I have given in your group. You see the formula, because next problem you have to solve by yourself. See the formula, see the procedure.
Hello, sir.
Yes, yes.
Sir, attendance. Attendance.
Attendance I will give you at the end of second class.
Oh, thank you, sir.
I hope all of you have written down the formulas and things, because next problem I will give you and you have to solve it.
Sir, can you please scroll up?
Can you please what?
Scroll up, man.
Up. Okay.